Hello everyone, good morning. This is Dr. Leema Rose, Professor, Department of Civil Engineering from SRM VEC Engineering College. Now we are going to talk about slope and deflections. Slope and deflections are very important in the beam members because they directly indicate how a beam behaves under the load and whether it is safe and serviceable. For the structural safety and serviceability requirements, slope and deflections are very important. So now we are going to see about the slope and deflections. So what is deflection? The vertical distance in a transverse direction between the position of axis before and after loading at that section of the beam is defined as the deflection of that section. That is, when a structure is loaded, may it be a beam or slab, due to the effect of loads acting upon it, acting upon it, it bends from its original position. This is what the original position. After subjected to the loading, it bends from the original position. That is, before the load was applied, it is original position. It means the beam is deflected from its original position is called as deflection. Slope. Slope at any section in a deflected beam is defined as the angle in radians which the tangent at the section makes with the original axis of the beam. That is, the slope at the deflection is the angle between the initial position and the deflected position. This is the slope. Theta b is slope, delta b is the deflection. The basic differential equation of elastic curve for slope and deflection is sigma by y equal to m by I equal to E by R. So sigma is nothing but the stress, y is deflection, m is bending moment, I is moment of inertia, E is Young's modulus, and R is the radius of curvature. So this is the differential equation of the elastic line for a beam subjected to the bending in the plane of symmetry. So the differential equation of elastic curve, that is the basic differential equation is EI into d squared y by dx squared equal to m. So this is what the basic equation we are going to utilize for all the computation, only this basic equation. So m equal to EI into d squared y by dx squared is the basic differential equation. So from this equation we can derive the relationship between shear force, bending moment and the deflection. So once you differentiate this basic equation, we will get dm by dx equal to EI into d cube y by dx cube. That is what the shear force. Dm by dx equal to shear force. So shear force will be equal to EI into d cube y by dx cube. Once again you differentiate this, we will get EI into d power 4 y by dx power 4 equal to differentiation of shear force. Differentiation of shear force gives the load. So once you differentiate this basic equation, we will get shear force. Once again you differentiate this, we will get the load. So once you integrate that basic equation EI into d squared y by dx square, we will get the slope dy by dx. Once again you integrate this, we will get the deflection. Therefore, y is the deflection of the loaded beam. Then the following important relationship can be arrived. As I told you earlier, the bending moment equal to EI into d squared y by dx squared is basic equation. Once you differentiate, you will get shear force. Once again you differentiate this, we will get the load or intensity of loading. So once you integrate this basic equation m equal to EI into d squared by dx squared, we will get the slope. Once again you integrate this, we will get the deflection. So this is the basic relationship between the shear force, bending moment and the intensity of loading. We have many methods for finding the slope and deflection of the beams. First method is double integration method, moment area method, Macaulay's method, conjugate beam method, and strain energy method. First, we will see about the double integration method. The double integration method is the powerful tool in solving the deflection and slope of the beam at any point, because we will be able to get the equation of the elastic curve. So the basic equation is A into d squared y by dx square equal to bending moment m. So from this basic equation, first we need to integrate the differential equation. Uh, and we need to apply the boundary condition to determine the constant of integration. From the first integration gives the slope, and the second integration gives the deflection in the double integration method. So we will consider an example, a simply supported beam with a central point load. So consider a beam AB of length L and the central point load W, subjected to a central point load W. So consider a section XX at a distance small x from the B. Let RA be the reaction at A, RB be the reaction at B. So this is simply supported with the central point load. First we have to calculate the reactions. So this is simply supported with the central point load. So automatically we will get the reactions W by 2 on both the sides. So RA will be equal to RB will be equal to W by 2. So we need to calculate the bending moment at X. So the moment at X will be equal to RB into X. So RB is W by 2. So W by 2 into X. So Wx by 2. So we know the basic equation is Ea into d squared y by dx squared equal to bending moment m. So we need to substitute the bending moment value. So for our case, simply supported with the central point load, the bending moment is Wx by 2. I'm substituting this value into the basic equation. I'm getting Ea into d squared y by dx squared equal to Wx by 2. Once you integrate this equation, I'm getting Ei into dy by dx equal to Wx square by 4 plus C1. C1 is the constant of integration. Now we need to apply the boundary conditions at x is equal to L by 2. The slope dy by dx equal to 0. So while substituting this boundary conditions, we are getting C1 equal to minus WL squared by 16. So by substituting this value, we are getting Ea into dy by dx equal to Wx square by 4 minus WL square by 16. So this is the required equation for the slope at any section. It will be interesting to know that the maximum slope occurs at the A and B. That is at the supports. Thus, for the maximum slope at B, so we need to substitute x is equal to 0. Why? Because at x value is 0, that position. So the EI into slope is notated it as IB. So which is equal to minus WL squared by 16. This negative sign indicates the in the anti-clockwise direction. So for simply supported with a central point load, the slope will be equal to WL squared by 16 EI. Once again you integrate that basic equation, we are getting Ei into y equal to Wx cube by 12 minus WL squared by 16 into x plus C2. Now again we need to apply the boundary condition at x is equal to 0, y equal to 0 and y equal to 0. Substituting this boundary condition values, we are getting C2 is 0. So substitute Ct equal to 0, we are getting Ei into y equal to Wx cube by 12 minus WL squared by 16 into x. So once you substitute the x value, x is equal to L by 2 in this above equation, we are getting the deflection will be equal to WL cube by 48 EA. So this negative sign indicates the deflection is in the downward direction. So for the simply supported beam with a central point load, we are getting the deflection is WL cube by 48 EA and slope is WL squared by 16 EA. So the double integration method is one of the easiest and user-friendly method. So we will see some other cases in the next classes. Thank you. Thank you all for your valuable time. Thank you. Thank you.